Hi, welcome to this video. And in this video, I'm actually going to be measuring milk shortly, and I'm discussing developing electrochemical assays and biosensors for measuring analytes in milk. So definitely give me 30 seconds and you'll be seeing me doing probably a couple of measurements. To kind of give you a sense of the workflow, I'll actually be measuring on some of this energy drink that I have in front of me, and I'll also be making some measurements on some of this milk that I have in front of me. If you do have any questions regarding this, you'll be able to find us on the website through this contact us button here. With that said, let me go through to that second camera and give you a quick kind of talk and demonstration of what we're actually up to this afternoon. So the first thing I want to do is I actually just want to show you the general workflow. So an assay that we already have is we're able to take an energy drink, and in this particular case, it's a Red Bull energy drink, and I'm going to measure the caffeine in it. I do want you to know that stay watching, because I will actually do some measurements on milk as well. I poured out some milk from this carton. When I say this carton, I realize that's not showing, but I did pour out some milk from this carton earlier on, and I will be making some measurements on it. It's actually quite good because I realize this is whole fat as well, so people sometimes get, let's not say worried, but thinking about all the extra interferences in milk. Okay, so what I'll do is I'm just going to change mode on my SenseItAll app. So now what I'm in is a caffeine measurement mode. As I say, stay tuned for the milk, but what I'll do is just to kind of give you a sense of the workflow that if somebody came to us and said, I want to make a assay for milk, how could you do it? How would you do it? I'll show you an assay that we do have. So I'll take 100 microliters of that energy drink. I'll throw away the pipette tip. I'll take 100 microliters of a buffer. So this is one of the assays that we already have, and we have a sort of buffer already to go on that. As I say, I'll take 100 microliters of a buffer. That's interesting. All right, so I've did the two. They went both into that tube. I'll just put that down for 1 second. I'll just clip the lid shut, and I will grab a sensor. Grab one of these, and I'll put that onto there. Good. I'll close that up a little bit. What I'm now going to do is I'll grab 50 microliters of that sample. I'm just going to make sure I name this in the app so I can actually find it. So I'll call this Red Bull. I'll call it 1 so I can find it. Done. Right. Okay. So first of all, I'm going to just show you a kind of an assay that we do have, but use it to kind of then make the milk measurement, but use this assay to kind of illustrate the kind of workflow that one can otherwise expect. So I'll take the sample, I'll put the sample onto the sensor. This is the good thing, and you'll see the milk. Milk is actually quite a complex sample, and it's also very opaque, so you'll see a kind of nice illustration in a minute, or in fact demo I would say, of how we can actually take a complex sample like milk. Not to say that Red Bull itself is not complex, but it's coloured and transparent, so you could argue that it's a little easier than milk itself, which is full of fats and proteins, but you'll see that we can actually deal with milk. Now it's done the assay, and what it will then do is, as it does that, I will just share my screen with you, because we have a system. In fact, it's giving me the answer now, which is just perfect, really. It's giving me the answer, and I'll just go to a slightly bigger camera, which is 0.29 milligrams per gram. And you can look it up, and 0.29 milligrams per gram is just a shade off 3%, and that's, or 0.3%, which is what Red Bull actually is. That's for caffeine. Let me just 0.3%, 0.03%. We're right. Let me just share this with you for 1 second, which I will do here. I just want to kind of show you that, in fact, if I just do a quick refresh here, I may make that a little bit more obvious in a minute. In fact, here's the Red Bull here. It's great. We get the time, the date, who did the work. Nice caffeine peak here. nice identification of the caffeine peak, nice result, ability for, let's say the Red Bull manufacturing quality manager to kind of, not that, to download, for example, and actually get, a nice report on that. So result on phone, which I will emphasize now. So lovely result on phone. No issue. You can just, anyone can sort of write that down. But if they want a little bit more of an insight on that, they can also get the results in the cloud as well. Time, date, operator, raw signal, and result all saved up into the cloud. And they can also get nice reports as well. So that's the kind of workflow. Now what I'm going to do now is go to the main, let's say, thrust of what I was going to demonstrate, which is actually talk about detecting analytes in milk. I'm going to talk in a very generic way, but I'm going to just take out that sensor, really put it out of my way, otherwise I'll end up reusing it. So what I want to now do is kind of show you how we could take that workflow that I just showed you and then deal with different types of matrices. So what I want to do is I just want to grab, and I'm making this up as I sort of go along, but 100 microliters of milk, in it goes, great. I want to do 100 microliters of buffer, great. Whether we need this or not will depend on, what program people actually bring to us. So I put those two things together, milk and buffer. You can see them in here. Now I'm just going to mix these two things up. Right, I've mixed them up now. What I'm going to do now is I'm going to go into more of a development mode. So earlier on I was in an application mode where I was measuring the caffeine in that energy drink. But now I'm actually going to go into more of a development mode. I'm just going to scan a QR code. I want to get that one. Yeah. So I've gone into what's called open circuit potentiometry. There's lots of ways of doing analysis using the SenseItAll platform, but I sort of, I'm just kind of doing a mock-up, let's say, of an experiment. So what I want to do is, in fact, this is milk, so I'll name it milk, so I can find it, milk 2, that will help me find it. I'll go continue. I just want to do an assay for, the good thing about ZP is we do try to think about the user experience, so I'm going to set this user experience to be kind of fairly quick. 60 seconds, that'll do. Right, I'm almost ready to go. I just want to think a little bit aloud, actually. I want to take that sample. So let me just take that sample. Again, see, I mean, this is a real world sample. It's pretty opaque. I'm going to put the sample on there. So it doesn't require a lot of material. That's always a good advantage with electrochemical techniques that we like to sort of run at ZP. So what I'm now going to do is I'm going to go continue, and I think I'm good. So this is nice because what it does is it kind of grabs raw data and sort of gives me this sense that actually, the whole system is working as you would expect. But I'm just going to show you at the moment that we can detect analytes in milk. Now I'm doing I'm doing a synthetic experiment here, but in a minute, when it kind of gets to around about 30 seconds, I will add in a few drops of analyte here. 3, 2, 1. Right, so I added that in, and you can see that the signal changed accordingly. And I'm just doing it to kind of illustrate the fact that we can definitely detect things in complex matrices like milk. And actually, I would say that electrochemistry is one of the best sciences for doing that. Real world samples. In fact, why is every glucose strip that a diabetic uses for testing their blood glucose electrochemical? Because it's actually very good at dealing with complex samples. Now, it said the same thing here. See, it said upload complete. So what does that really mean? Well, what it means is this, that if I go up to here and I go out of my Red Bull data and I go and have a quick look at here, I'll just do a refresh here. So then if people come to us and say, okay, I want you to develop me a new assay, we would, start doing some lab experiments. But of course, a real person, let's say a real technologist in a food production, can't necessarily deal with that. That might be an interesting signal, but it doesn't really help them that much. But what we would end up doing is very quickly then being able to take that signal and start training our database to essentially deal with it. So if I go peak height, I'll choose 50 seconds. I'll tell it, I'm just making these numbers up, by the way, but I'm just going to kind of convert that analyte. My dilution was actually 2. So this just allows me to go very quickly from a raw signal, which means nothing to anyone. In fact, now you can see that now I've actually selected that. I just need to do one more thing, which is show extracted value. And I'll close that. I just wanted to do one more thing. So now I've actually turned it into, in this case, a millimole concentration. I think if anything's in 58 millimole, it's quite high. So in fact, I'll just turn down that sensitivity slightly by going 10. In fact, yeah, let me just try 20 for a second. Just want to have a quick look. Yeah, so bring it down to 29 millimole. That's just a proof of principle. So what I've tried to show you here is a standard assay that we do have, which is, for example, and at ZP we develop assays for people so they can measure real analytes in real samples. So I did the Red Bull because that's something we've already got. But then I think there's also an interest in potentially measuring analytes in milk. And that's why I then did the milk demo. And just to show you that we can get chemical signals out of real samples like milk, and I don't actually think it's that much of a problem. So if you've got any questions, don't hesitate to reach out to us on the website. Okay, thanks very much.